So, instruction set of 8086. So, if it supports 6 types of instructions. So, just like other processors that we have seen, it supports a good number of instruction types. They can be grouped into data transfer instruction, arithmetic instruction, logical instructions, string manipulation instructions, process control instruction and control transfer instruction. So, some of them are common to us, they are well known to us like data transfer, arithmetic, logical, etc. Whereas, string manipulation instructions, so they are something new, and this process control instructions. So, there will be some instructions which are new to us, and this some control transfer instructions will also different types of branches, calls, etc. So, they are processor specific. So, we will see that. The first category that we have are the data transfer instructions. So, these instructions are used to transfer data or address into registers, memory locations and IO ports. So, they involve two operands, now a source operand and a destination operand, and the operands are of same size. Now, in case of 8086, the source can be a register or a memory location or an immediate data, and the destination can be a register or a memory location. Naturally, destination cannot be a immediate data, cannot be an immediate data. There is another restriction, like you cannot have both source and destination as memory. So, you cannot have an instruction where this you cannot say like move say bx comma si. So, this is not possible. Here what I wanted to mean is that memory location bx gets the content of memory location si. So, that is not allowed. So, I can have source as a register, destination as a memory, or so this is one possibility, source as a register, destination as a memory, or I can have source as a memory and destination as a register. So, that is possible, or source as an immediate operand and destination as a register or destination as a memory, but I cannot have that source as a memory. So, this is also memory and this is also memory. So, that is not possible. So, you cannot put both of them as memory, and definitely the size matters. So, size should be same. So, there should be either a byte or a word. One 8-bit data can only be moved to 8-bit register or memory, and a 16-bit data can be moved to 16-bit register or memory. So, that is obvious. So, if you look into different category of data transfer instructions, in the first category we have got to move register to memory, or and first operand is register, second operand is memory, or first operand is second operand can be register or a memory. So, move register 2 comma register 1. So, register 2 gets register 1, memory comma register 1. So, memory gets the content of register 1, or move register 2 comma memory. So, from memory it comes to register 2. So, as I was telling, so there is no instruction like move memory comma memory. So, that is not there. Okay. So, we cannot have both the operands as memory. Then we can have for immediate, so move register or memory comma data. So, this is the immediate mode. So, you can move some immediate data to a register or a memory location. So, you can have in that category you can have data movement to register or data movement to memory. There is another instruction which is not there in say 8085 type of processors too much, which is the exchange. So, it will exchange this content of two registers or a memory location and a register. So, this exchange register 2 register 1, the content of those two registers will get exchanged. Okay. Or we can have this exchange memory comma register 1, the content of this memory location will get exchanged with register 1. So, this way we can have this exchange instruction. Now, this exchange instruction, so apparently it seems there is no point having such an exchange instruction, because this exchange is equivalent to moving first this register 2 to some temporary register, and then from then register 1 will get the content, register 2 will move it to this register 1. We can put this we can send this register 1 to register 2, and then finally, the register 1 this t value, the temporary value can be moved to register 1. So, that way this register 1 and register 2 content can get exchanged, but the point is if we are trying to do this, so that means it requires 3 instructions. Okay. And this creates difficulty in many cases for the operating system designers, we need some facility by which in a single instruction we are able to read the content of a memory location and change its content. Okay. So, for that type of instructions, for that type of facilities, so this multi byte or multi instruction solution, so they are not correct. Okay. So, we need to have single instruction which will be able to do all these things. So, that is why these exchange instructions may be useful for them. So, this has been introduced for this operating system design purpose. Next, we will look into the other data transfer instructions like push and pop instructions. This push instruction, so this works with push register 16. So, the 16 bit registers can be pushed, like you can have like push AX. So, you can have instructions like say push say BX. So, this BX register content will be pushed. So, first this stack pointer is decremented by 2, and then this memory address effective address is formed by SS stack segment multiplied by 16 plus this stack pointer. Then this higher order byte will go to this memory address S, and this lower order byte goes to MAS plus 1. That way the two successive bytes they will be saved. And then with similarly the push memory. So, we can also have this push memory. So, here this so this is for here also it is the stack pointer is decremented by 2, then this memory address is formed, and then the 2 bytes from the starting at this memory location will be pushed into the stack. And we have just the reverse of push, the pop instruction. So, here the only thing is that the stack pointer is incremented by 2 after getting the content from the stack. So, this register 16, so it will be the content will be coming from this these two locations from the stack, and then the stack pointer will be incremented by 2. And similarly, if it is a pop memory, here also the same thing. So, content from these two stack memory locations, they will come to the memory address specified here, and then the stack pointer will be incremented by 2. So, we can have this push pop also for this data transfer. Then other instructions that we have is the input part, by which you can read some port, and the output part by which you can transfer some output to the output port. So, in A comma dx, so this is for 16 bit. So, this as you know that we said it is for 16 bit port address. So, 16 bit port address. So, this is indirect one, indirect address. So, port address this dx value will be put onto the address bus for port address, and this content of that particular port will come to the AL register. And this instruction, so it is the destination, since this is AX. So, it is taken as the port to be 16 bit. So, it is expected that on getting this dx value onto the address bus, the port will get selected, and this 16 bit port value will be coming to the AX register. Okay. And so for 8 bit port address, so we can specify it directly. So, address 8. So, this is an 8 bit immediate value. So, we can directly specify some 8 bit port address there. So, this is the direct port access, and that is indirect port access. So, in AL comma address 8, so as a result from that port, the value will come to the AL register, and move in AL comma in AX comma address 8. So, the 8 bit port address is put, but the port is a 16 bit port. So, port is a 16 bit port. So, it gives 16 bit value onto the data bus, and that comes to the AX register. And just like in, so we have got out instructions. So, out dx comma A type of instructions, or out address 8 comma A type of instructions. So, they are just counterparts for the in instructions. Next, we have got the arithmetic instructions. So far we had this data movement instruction or data transfer instructions. Now, we have got arithmetic instructions. Now, in arithmetic instruction, we have got the add as the first exemplary instruction. So, we can have these operands like register 2 and register 1 as the two operands, and the meaning is that register 2 will get the content of register 1 plus register 2. The flags are affected it is not specified here directly, but while discussing the status flags. So, we have seen that the flags will get affected by doing this operation. So, this similarly the second operand can be memory also. So, also you can have like add register 2 comma memory. So, register 2 gets register 2 plus memory. So, you can have at least one of the operands as a register. So, both the operands cannot be memory. So, here the third instruction you have got add memory comma register 1. So, memory gets the content of memory plus the register 1. So, memory can be specified, it is an address specified in different modes, okay, that we have seen previously. Then we have got immediate addition. So, add register comma data, where data is an immediate data. So, register get register plus data, or you can have add memory comma data, where the memory content will be added, and the data will be added with the memory content, the immediate data will be added and the content is updated. And we can have this add a comma data. So, directly we can specify this immediate value AL and AX. With AL this 8 bit data will be added, or with AX this 16 bit data will be added. Then there is ADC, that is add with carry. So, similar to add, but it is with the carries. Okay. So, carry flag will also be added. So, this is register 2 will get register 1 plus register 2 plus carry flag. So, otherwise it is same as add, but this carry flag will also be added within the summation process. Then the subtract instruction SUB. So, here it is again similar to this add instruction, but this is for example, this sub register 2 comma register 1. So, it will register 2 will get register 1 minus register 2. So, otherwise it is same. So, whatever we have got for add, the same is true for sub, and of course, the flag settings will be different. So, overflow 0. So, they will be set depending upon the content that you are getting there. Then subtract with borrow, just like we have got add with carry. So, we can have subtract with borrow. So, the operation is register 2 gets register 1 minus register 2 minus the carry flag also. So, as a result, this is the carry is also subtracted. So, borrow is also subtracted. So, if you are having say multi byte addition or subtraction, then this ADC and SBB instructions may be useful, as we have seen previously, that for multi byte addition. So, from 1 byte addition some carry or borrow is generated, and then that is taken in the next byte while adding or subtracting the next byte. So, we can take this carry or borrow into consideration. So, that way we can have this subtract with borrow type of instructions useful. Then there is increment instruction. So, this is just incrementing some register by 1. So, increment register 8. So, this will be incrementing register 8 by 1 bit, increment register 16. So, it will increment register 16 by 1, not 1 bit, by the value 1, and increment memory. So, this will increment the memory location by 1, and just the opposite of increment we have got the decrement instruction. So, decrement register 8 will decrement the register 8 by the 8 bit register by 1. So, like that you can specify any 8 bit register here. So, that value will be decremented. Then the multiply instruction. So, multiply register. So, what will happen is that AX register will get AL content of AL into register 8. So, this AL register should for multiplication there are two numbers that we want to multiply. So, the first number should be in the AL register, second number you can put it onto some register and mention that register name. For example, you can say like say MUL, you can say like MUL say CL. So, what will happen in the AL register I have some content. So, that will be multiplied by the CL register, and the result. So, both of them being 8 bit register. So, this result is a 16 bit register value, and this out of this 16 bit this AX register will hold the this AX register will hold that 16 bit. So, out of that AL will hold the lower order 8 bit, AH will hold the higher order 8 bit. Now, if the operation is on 16 bit multiplication, like if you say like the instruction is say MUL CX. So, instead of 8 bit is 16 bit multiplication. So, it is expected that the AX register holds the other operand and Cx is the other registered operand that we have. So, it will do like Ax will be multiplied by Cx. So, as a result this multiplication will produce a 32 bit output. So, in the out of this 32 bit output, the Dx register will hold the higher order 16 bit and the Ax register will hold the lower order 16 bit. So, that is how this multiplication instruction will take place. Then there is imul instruction. So, this will be the integer multiplication. So, it will be doing this multiplication. The operation is similar, but it is just for the integers. So, similarly, we have got this division operation. So, division with register or memory. So, this division, so AL will hold this X divided by register 8. So, this is the quotient part that will be going to the AL register and the AH will get the remainder part. So, AX mod register 8. So, that will go to the AH register. So, this whatever register is specified. So, that will be used to divide the content of AX register and the AL register will get this quotient part and AH register will hold the remainder part. For 32 bit division, so this quotient the dividend is contained in Dx and Ax pair. Dx will hold 16 bit higher order 16 bit, Ax will have lower order 16 bit and that is multiplied by that is divided by this register 16. Like you can say write like something like say div, you can say like div Bx, with a 16 bit division. So, what it will do? So, Dx colon Ax, so that will be divided by Bx. So, this will produce the quotient and the remainder part. So, the quotient part will go to the Ax register. So, this will be available in the Ax register and the remainder part will be available in the Dx register. So, this way it does the division. Similarly, instead of register, so you can have this memory operand also and otherwise it is same, the operation is similar. So, we have got this other division also, this IDiv instruction for this another division operation that we can have there. Then we have got the comparison instruction. Then this comparison instruction, so it will compare two registers or one register with a memory location. Okay. So, but you cannot have the same thing, that is you cannot have both the location, both the operands as memory. So, that is not possible. So, the flags will be modified like say compare register 2 comma register 1. So, what it will do, the modified flags, so that they will depend on the value of this register 2 minus register 1. If register 2 is greater than register 1, then carry flag will be 0, 0 flag will be 0 and sign flag will also be 0. If register 2 is less than register 1, in that case carry flag is 1, 0 flag is 1 0 and the sign flag is 1. So, basically so by this we can check for this less than condition after this comparison. So, if you put a jump on less or something like that, then if this carry flag and sign flag they are set, that will mean that there is an there is a comparison where register 2 was really less than register 1. And for equality condition, this carry flag is 0, sign flag is also 0 and the 0 flag is set to 1. So, with that you can have instructions like jump on 0 and all that after the comparison instruction. So, rest of the thing they are similar. So, we have got this comparison with one of the operand may be memory for the comparison operation. So, you can also have comparison with immediate data like compare register comma data, where this data is an immediate operand. So, you can do this comparison like if register is greater than data, then this same flags will be set like this. If it is less than data, then the flag setting will be like this. So, this way we can have different flag settings, okay, and we can have this comparison instruction for the arithmetic operation. For immediate operand, so again the two things, you can have an 8 bit data or you can have a 16 bit data. So, for 8 bit data, so we can have instruction like compare AL comma data 8. So, that way we can have some 8 bit data there. So, again the operation is similar. So, AL minus data 8 will be done. If AL is greater than data 8, then the flags will be set in some fashion and otherwise the flags are set in different fashion. So, as it is specified here. So, if this if you are specifying this AX, then you can have 16 bit comparison also, that way it is very much flexible, both 8 bit and 16 bit comparison can be done. Next, we look into the logical instructions. So, logical instructions where we are doing the logical operation like AND, OR, XOR, testing, shifting and all that. So, the first one, the AND operation. So, AND A comma data. So, this will do ANDing of A with the AL register with some data 8, like say 8 bit data. So, AL will get AL and ANDed with the 8 bit data, so that under the immediate mode, or 16 bit data under the immediate mode AX and data 8. So, for OR instruction, so again the same thing, we can have this register 2 or memory, or we can have it like this register 2 memory. So, they will be ORed, these two register contents will be ORed and the result will be available in register 2. So, you can have this that immediate data also, like you can write like OR register or memory comma data. So, you can say like OR say AX comma some 16 bit data. So, that 16 bit data will be ORed with this register bit by bit and the result will be available in the AX register. So, this way we can have this OR with 16 bit data, or if you are directly writing. So, instead of writing register, so you can also take this value to AL register and CX AX registers for doing the 8 bit operations of this OR. The next important category of instructions that we have, so that is the string manipulation instruction. So, this is a new instruction that type that we category that we have in 8086. So, string is any sequence of bytes or words. So, unlike say what we know about a string, that is the character string or things like that. So, in case of 8086 processor, so it cannot distinguish between numbers and characters. Okay. So, that is why it any sequence of bytes or words, so that is taken as a string. So, this instruction set, it includes instructions for string movement, comparison, scan, load and store. So, these are the various string manipulation instructions that are available in the 8086 processor. There is one REP instruction prefix, repeat instruction prefix. So, it is used to repeat execution of string instructions. So, if you say REP, then the instructions will be repeated, execution of the instruction will be repeated. Then string instructions that end with S, SB or SW. So, S like move is the normal movement between registers, moves is the string movement that way, and moves B is the byte movement, and moves W is the word string movement. So, we can have this moves B, moves W like that, then CMPS, CMPS B, CMPS W like that. Offset or effective address of the source operand is in SI register and that of the destination operand is in the DI register. So, we have got this SI DI register pair, so which are holding the source and destination addresses. Depending upon this the status of this direction flag, SI and DI registers are automatically updated. So, after every byte or word transfer, this SI and DI registers, so they will be updated automatically. So, DF flag, if it is, so that will tell us the direction and based on that it will be updated. If DF equal to 0, then this SI and DI they are incremented by 1 for byte and 2 for word. So, if it is moves B type of instruction, then after doing one transfer, this SI and DI will be incremented by 1. If it is moves W type of instruction, then it will be updating by 2, incrementing the value by 2. And if DF equal to 1, then instead of implementing it, the values will be decremented. Okay. So, this way we can have this string manipulation instructions. So, this REP prefix, so this REP prefix can be the REPZ or REPE. So, it is repeat the compare the CMPS or SCS scan instruction till Z 0 flag equal to the ZF flag becomes equal to 0. So, while CX not equal to 0 and ZF equal to 1, so it will repeat the string instruction. So, and after that after every transfer this CX bit will be updated. So, CX will be updated to CX minus 1. So, this using this repeat construct, so we can just repeat prefix. So, we can repeat this compare or scan instructions. Similarly, REP-NZ, so repeat this CMPS or this SCAS instruction until this 0 flag is equal to 1. So, until ZF equal to 1. So, it will go on repeating the operation, and after every execution, so it will decrement the CX register value by 1 in both the cases. So, the moves instruction, so we have got two variants, moves B and moves W. So, for the moves B instruction, what happens is that the memory address is computed as DS into 16 plus SI for the source part. For the destination part, it is MAE, which is ES into 16 plus DI. Then MA, the content of memory location MA is transferred to the memory location MAE. Now, if DF equal to 0, then after doing this transfer, so DI value is incremented by 1 and SI value is decremented by 1, and if DF is equal to 1, then DI and SI, those values are decremented. Similarly, this moves W instruction, so this is similar to moves B, but this incrementing and decrementing, so 2 bytes will be transferred, like this MAE will get the content of memory location MA, and memory location MAE plus 1 will get the content of memory location MA plus 1, and after that this DI and SI values, they are decremented or incremented by 2. So, this way this moves instruction can be useful. We have got CMPS or compare instruction. So, this CMPS instruction also has got two variants, compare CMPS B and CMPS W. So, CMPS B, the address calculations are same as the moves instruction. So, this MA and MAE values are calculated, and then the ASCII values of those locations are compared. So, if MA value, content of memory location MA is greater than content of memory location MAE, then this will be the flag setting. If MA is content of memory location MA is less than content of memory location MAE, then this will be the flag setting. So, this way we have got different flag settings, and then for the byte operation, these DI values will be updated by 1, and for by word operation they are updated by 2, and depending upon the DF bit. So, this updation may be an addition or updation may be a subtraction. If DF equal to 0, the value may be incremented, DI and SI values may be incremented, and if DF equal to 1, then this DI and SI values may be decremented. So, this way we can compare between byte, string byte or string word. Then there is a scan instruction. So, scan a string byte or word with accumulator. So, SCAS B. So, SCAS B, what is it doing? So, here it is only this destination address is taken. So, ES colon DI. So, that address is computed. So, that is MAE, and then it will be compared with the AL register. So, it is not compared with any other source block, but it is compared with the AL register. So, basically in the AL register you can put a particular character and you can try to scan for that character into a string. So, that is very common operation to find the occurrence of a character in a string. So, that can be done by using this SCAS B instruction. So, if AL is greater than MAE, then this is the setting. So, the comparison, standard comparison. So, if they are same, if the character matches with the AL, then this 0 flag will be set. So, you can compare this and get the matching, and if DF equal to 0, then DI will be incremented, if DF equal to 1, DI will be decremented. And we also have a 16-bit comparison. So, SCAS W. So, here this AL, this AL will, so this is AX will be compared in fact with this AX and MAE, and then if AX is greater than MAE and MAE plus 1, so then these flags will be set. Okay. So, this content should be, so this one should be this should be AX minus MAE colon MAE plus 1. So, these two values should be compared, and if AX is greater than this quantity, then the flag setting will be like this, otherwise the flag setting will be the otherwise. So, this way you can have this SCAS instruction for doing this memory operation, this string operation comparison and all. Okay.